Let's continue with Riemann sums. Last time we learned how to find the precise area under the curve using Riemann sums. We're going to continue doing that, but we're just going to look a bit more at the notation and the terminology. This is what we did last time, right? And we got to this notation, that's sigma notation. And now we're going to define a term that will guide us through the rest of Calculus 2 if you wind up taking Calculus 2. The definite integral of a function from a to b is the net area under the curve, defined as the integral from a to b of f of x dx, which equals the limit as n approaches infinity of the sum from I equals 1 to n of f of, and instead of writing all this a plus I delta x stuff, the book just writes xi star. And I'm actually just going to go ahead and reduce it to f of xi times delta x. The book uses xi star for technical reasons, but I'm just going to write it as xi, where let xi equal a plus I delta x. Okay. So that's our notation. So for example, if I said write this as a Riemann sum, you'd write this as, okay, well, this guy is going to equal, well, I guess I do need to write the limit as n approaches infinity. So let's see what this is going to be. It's going to be 5xi to the 6th minus 4, and then all of this is being multiplied by 8 minus 5 over n. So I wanted to reduce it, I could write it as 3 over n. That would be my, sorry, and I forgot that pesky little thing called sigma. Sorry, we definitely need that. All right. There we go. Now you could go the other way too, right? You could have this mess of a limit, you know, in Riemann sums and have to figure out what that's the integral of. And so this is going to wind up being the integral from, well, it looks like we've got a equals 1 right here. Let me just highlight that. And it looks like our width is 2 over n. Maybe I'll... Let me see that over here. So I guess our endpoint is 3. And it looks like our f of x is going to be e to the x. So it looks like that's what we've got. Now let's look at a couple of properties. The integral is defined from going from the lower number to the higher number. If you see it in reverse, it's just negative. Okay? If you integrate something from 0 to 0, or sorry, from a to a, you're going to get 0. And the reason for that is that, well, just think about it. If you've got some kind of a curve here, and you're finding the area under just this one part right here, well, you get 0. That's the end of it. All right. You can, this is not completely obvious, I don't think, but you can show that you can split an integral up by each term. So, like, you can just, the sum of the integral of the sum is the sum of the integrals, right? It turns out a constant times the integral also works. And if you, let's suppose you're integrating some function from a to b, and then you decide to stick this third term c in here. Well, maybe you can see the area under this curve plus the area under that part of the curve is just the area under the whole thing, right? So the area from a to c plus the area from c to b is just the area from a to b of the curve. Okay. And let's do one more example. One more example, right? This is a little bit longer, right? The area is going to equal the limit as n approaches infinity of the sum from 1 to n of 3 times, so that's going to be, what is that? A plus I delta x. Now note that delta x is going to be 2 over n, right? Because delta x equals 0 minus negative 2 all over n, which is 2 over n. Remember, delta x is always positive, right? Squared minus xi. And then all this is being multiplied by 2 over n. Ugh, lovely. All right. So what we're going to do, we're just going to do this all out. Simplify a bunch of stuff. Keep this limit of the sum of blah, 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 blah. First off, we're just going to multiply all this out, right? Just FOIL it. We get 4 minus 4. Let's put it like this. Yeah, I guess I'll put it like this. Minus 4 over n. Oh, nope, I lied. It's actually minus 8 over n I plus I squared times 4 over n squared. So this became this. Okay. And then there's going to be plus 2 minus I, or I guess times 2 over n. And then this is all times 2 over n. Okay? So when we do this out, multiply through by that 3, wind up getting a whole bunch of stuff, right? 12 minus, I actually put the, I guess I'll make this 24 over n I plus, I'll put the 4n squared in front of the I squared. And then this is going to be plus 2 minus, I'll say 2 over n times I. And then this is all times 2 over n. And then let's see, why don't we multiply, first of all, let's combine some like terms, right? Let's combine the 12 and the 2. Let's combine the 24 and I, that, okay. So let's just get limit as n approaches infinity of the sum from 1 to n of, let's see what we get here. Oh, I forgot to put that there. Okay, so this is 14 minus 26 over n I plus 12 over n squared I squared, all times 2 over n. And then if we multiply everything by 2 over n, we get, let's see, that's going to be 28 over n minus 52 over n squared I plus 24 over n cubed I squared. And at this point, we can pull this trick. And we can say this is going to be 28 over n. Oh, no, this is just times 1, sum of 1. I guess it's minus 52 over n squared times the sum from 1 to n of I plus 24 over n cubed times our sum from 1 to n of I squared. Whew. Writer's cramp. Okay, and then at this point, we just use our counting tricks, our little identities, which again, I will give you on a quiz or an exam. But here's where we substitute our stuff in. And And so when we take our limits, right, and first one should be pretty straightforward. It's just 28. But we wind up getting 28 plus 52 over 2 plus 24 times 2 over 6. And we can simplify this, so we should. 28 plus 26 plus 8. All right, 28 plus 26 is 55. So I think I'm getting 62. And that's our answer.